I'd like to go through an example of how we can actually talk about two-dimensional vectors, and I'm going to try to use a real-world scenario that you're ideally familiar with, which is campus. So eventually we'll be talking about vectors really within a physics context, but right now I want to start with something simple, which is finding your way around campus. So the first thing that you need to do is know your coordinate system. Now I realize that many of you haven't spent a lot of time looking at campus from the air, and so briefly we have our science center here and the science quad here. Evans is up here, and the main quad is here. So that's kind of the map that we're looking at. But when we talk about the coordinate system, we actually mean what directions are we talking about. So north in this case is up on the screen, but something that's important to remember is if I'm standing in the room, north is actually that way right now. Up is that way. North and up are not actually the same directions in the real world, but at least on this screen, it happens that north is up. But in the real world, those aren't the same. So with our coordinate system, we have north going this way, so east is over here, west is over here, and then south is downwards on the screen. The second thing to do is to define really axes and our origin. So in this case, we now could say that this is our north direction, east, and so on, and where those axes intersect is our origin. Now you can kind of choose whatever directions you want and whatever origin you want when you're solving a physics problem, but usually there's going to be something that makes sense. Given that we talk about maps in terms of north and east and the cardinal directions, those are a good choice here. But I could pick that origin in a different place. I've happened to put it right in front of the library, but I could have chosen to maybe put it on the science center. That doesn't matter. But you need to specify what your origin is to make it clear how you're approaching your problem, since different people might choose different origins. The next thing to do in this case is we're going to talk about making a position vector. So we need to talk about a position to something. You want to talk about a specific object at a specific moment in time. So I might talk about you being in the science center. I might know that during class time you are in fact in the science center. But you're not always there, and not all people are there. But at a given moment in time during class, you're in the science center here. So to make the position vector, I actually am going to take a vector from the origin and point it to have the tip at you. Now one thing that I want to clarify here a little bit is that when I made these pictures, I'm using a paint program where I can't do really nice notation. So I've written it in this funny way here, but I could have also written that as R subscript 1, because this is the first position vector that I've drawn, but since it is a vector, I need to put the arrow above it. So this funny notation here is just one simple way of writing this in a program that doesn't let me do subscripts. So that's the position vector towards you. But now, let's instead think about a displacement vector. After you've had some classes in the science building, you're hungry and you want to go and have lunch. That's going to be at Evans. Now, Evans is, of course, in a different point on campus. It's also not at the origin, though. So we could have made a different position vector from the origin to Evans, but I'm not going to worry about that. I want to make a displacement vector that goes from you to where lunch is. And I simply do that by starting it, the tail of the vector, at your position and drawing the tip to Evans. Now again, this notation here, it's that I have a delta because this is a change in position, which is by definition a displacement. And again, you need to put a bar or an arrow over it to imply that this is in fact a vector. So now, what's important to remember is that that position vector started at the origin, but the displacement vector doesn't. That means the displacement vector is always going to look the same. It's going to have the same size, magnitude, the length, and it's going to have the same direction, even if you defined your coordinate system differently. So for instance, if I put my origin in a different place, for instance, Rebecca, maybe that's where you parked, then in that case, this vector still looks the same. It doesn't depend on the coordinate system. What this means is that sometimes, for instance, in motion diagrams, we're going to be drawing displacement vectors without clearly defining an origin, since if you only have displacement vectors and things related to displacement vectors, you don't need that origin. I'd now like to give you a chance to stop and practice this, to see if you kind of understand how vectors work. Now, the question here is which two buildings could this actually represent this vector? Now, what's important to remember is that a vector has a size and a direction. So you have to use this length vector, and you have to keep it pointed in the direction it's already pointed at. So then the things to think about is, does this represent Campbell, which is here on the map, to Evans, which is up here? Does it represent Evans to Campbell? Again, Evans to Campbell. Does it represent the main building to the Science Center, or perhaps the Science Center to the main building? Or could it represent Dana down here to the Alston Student Center over here? So pause the video, take a few seconds, make your decision, and then come back and watch to see what the correct answer is and why. Okay, the best answer here is B, that this vector represents Evans to Campbell. And what you can hopefully see is that this red arrow here has the same direction and the same size as the original vector that you were given. So it needs to point, in this case, slightly south and west, which would be from Evans to Campbell, and it needs to have this distance. Now, I haven't given you any sort of distance scale on this picture, so you don't necessarily know what this is in meters, but that needs to directly fit on top of the map, which it does. So for instance, A, which would be Campbell's to Evans, actually would be a vector pointing in the opposite direction. So even though it would have the same size, the direction is different, so it's not the same vector. So B is the situation where you would have this vector taking you from Evans to Campbell Hall.